Hello, this is Mr. McLeod, and welcome to Standard Point 1.3 for Earth and Space Science. This is going to look at star life cycle, uh, stellar evolution, stellar nuclear synthesis, and all of those things. So let's begin. It's going to cover the meat and potatoes, the stuff you really need to know. Okay, so first, if you look at the standard, it tells you need to communicate a scientific idea. So there's a few ways to do that. Okay, you could do it written, which is writing what you researched down in an organized format. It could be an outline, could be a paragraph, it could be a story, whatever, written. Okay, it could be bullet points. It just needs to be organized, and it needs to be coming from research information. Communicate a scientific idea verbally, so you use that research and you talk about it without the research present. So it shows me an understanding of the research, okay, understanding of the scientific ideas. So you need to talk about it, but you can't have something kind of telling you what it's about. Graphically, okay, this is basically using a visual format. It could be a graph, it could be a table, it could be an image, it could be a picture, it could be a drawing, to present information that you have researched. And the final form to communicate a scientific idea is mathematically, which is using formulas and equations and numbers to express research information. So most likely for standard 1.3, you will probably be doing written, verbal, or graphic type of communicating of your scientific ideas. And to achieve the 3 on the rubric, you will need to use more than one of these formats. So we had to get started before we get into the information. So you have to communicate the scientific idea to me. Okay. So now we're going to look at light spectra. It is the visible spectrum that is collected from objects. That's what the light spectra is. This visible light spectrum is a part of the EM spectrum. So why is this important? Using a star's visible spectrum, okay, scientists can determine the composition of a star and its motion. Okay, so it's very important that we use this visible light spectra. We can look at the star's signature, its fingerprint or footprint, to determine what the star is made out of, which is the word composition, or how the star is moving. So there's a few ways, a few links that we're going to look to help us out with this. Okay. So that is the spectrum of white light. That's all of the colors. Okay, and that's the visible light spectrum. So stars down here, okay, this is what we see. So we should see this, and we have this emission, so the absorption of the dark lines, the missing things, and that is the elements that are present. Those black lines represent the elements that are present. So this is a visible light spectrum. This is what we see when we look at stars. Each element in the periodic table can appear in gaseous form and will produce a series of bright lines unique to that element. Hydrogen will not look like helium, which will not look like carbon, which will not look like iron, and so on. So they're all unique. Thus, astronomers can identify what kind of stuff are in stars from the lines they find in the star's spectra. This type of study is called spectroscopy. So scientists of spectroscopy is quite sophisticated. From spectral lines, light given off at a specific frequency by an atom or molecule. Every different type of atom or molecule gives off light of its own unique set of frequencies. Thus, astronomers can look for gas containing a particular atom or molecule by tuning the telescope to one of the gas characteristic frequencies. Astronomers can not only determine but the temperature and density of the element in the star, which then they can tell us the density and the temperature of the star itself. So it's very useful to help study stars. Let's go to one more link that talks about light spectra. Okay, and this is hopefully something you saw in class. So this is a specific star's light spectra. We go down here, and it tells us the element-specific light spectra. And right, you have these notes, so you could go to these links on your own. And so now they gave us a mystery star, and we need to tell what type of elements are in it. Okay, looks like a big bold line here that isn't present anywhere else, so it's probably hydrogen. There's a lot of stuff going on here, so it's probably iron. Yeah, I don't see this bold line anywhere. This is a tough one. Probably has more than just hydrogen and iron in it. Doesn't. Looks like it might have magnesium. Yeah, we'll say magnesium. Let's see if I got it right. I feel like this is a tough one. I could have, might not have. Oh, it has hydrogen and iron for sure. Oh, it might have calcium as well. So let's see. Right. Wow. So they gave us one that had all 4 elements in it. And so you could see all the black lines, and so we can identify a star that way. Okay, and you can read the background on how this works here if you would like. Okay, so that's how a scientist used star light spectra to tell the composition of star, what it's made out of, like its elements that it made out of, and in its motion. We mostly talked about what it's made out of with those light spectra. But if those lines change, and they kind of tend to be going one direction or the other, we can tell if it's moving away or closer to us. And so we use light spectra that way as well. So now brightness of a star, what do we look at? So each star has its own observed brightness. And this brightness can be impacted by the composition of the star, the distance from the observer, and its motion from the observer. So all those things determine the brightness of a star. And we mostly observe stars from Earth. So let's click on this link and see what it tells us about the brightness. So the idea is astronomers are able to measure how far away a star is by using its brightness, okay, and then using something called a parallax, or triangulation, which is basically just trying to form a triangle. So that's Earth orbiting the sun at one month, and then this is Earth on the opposite month. We know the distance from the star, or the star's brightness, so we can use those lines, make triangles, and all of a sudden we can determine the star's distance. So we go back here, and the brightness of the star can give us an idea of the composition, and it can tell us motion, right? Clearly, if it's moving away from us, it's going to appear lighter. But we really use brightness to help us with distance as well. And so scientists study stars, light spectra, and brightness to determine the elemental composition of stars, the distance of stars, and the motion of stars. That's the first big idea. How do we study these stars that are in this universe? Okay, we can't feel them, we can't manipulate them, we can't touch them, all those things that we usually do for study things. So how do we do it? We use the star's light spectra and the brightness to tell us its composition, its distance, and its motion. Okay, So there are many different routes a star can take. But for the most part, a star's life cycle, so the life it goes through, it's not living, but it goes through a cycle of its life. Similar things happen in all stars. So we'll look at this link, see what it tells us. Okay, this is my favorite picture of a star life cycle because it tells us basically all of the images. So we start in this stellar nursery, with all of them become protostars, and now depending on how much mass the star has, it can be a blue supergiant, which is a ton of mass. It's a lot of matter all in one spot, or a brown dwarf. Okay? So if it's a huge star right here, okay, the most common two types are these two right here. Okay? It becomes this blue supergiant, and this is very rare. This is probably about like 1% of the stars in our universe. Okay, it becomes a blue supergiant, then it becomes a red giant. And then once it becomes a red giant, it might become a blue giant, or it might become something we call a supernova. And if it's a supernova, that means a star is exploding, and then it ends up as a neutron star. So there are things happening through these stars' life cycle that we're going to talk about. But it's important to know the different phases. Okay, so right up here, this group of here is about 1% of stars. And then about 99% of the stars are going to be an average star like our sun. So it has an average amount of mass. Okay, and so there's a star like our sun. It goes through its lifespan. And for our sun, this is going to be, okay, it's going to go here. Then it's going to turn into a red giant, which is a really big star. And then it will become a planetary nebula and end up as a white dwarf. So those are all the options. Okay, remember this one is about 99% of our stars, and this is about 1% of our stars. These down here are very rare. Okay, so we could study these stars in their life cycle, and we could produce something to organize them all into a diagram that we call the HR diagram. Okay, and you notice this is going to be organized by its temperature and its brightness. And you notice here is these are the supergiants over here, and these were the blue giants that we saw earlier, and they come really quickly into blue supergiants. But if they're not big enough, they just stay on this main sequence, like our sun does, which is right here. Okay? And what happens is they get to a point down here, and they then become these giants, these red giants. And that what this doesn't show is it's either going to become a red giant and turn into a white dwarf down here, or it's going to become a red supergiant and explode in a supernova. And so that is the Hertzsprung-Russell diagram, or the HR diagram, that allows us to see these stars organized as well as put them in their life cycles. So now we want to find out what happens during these star life cycles. Okay, it's important. So during this life cycle of the star, the star itself has this process called nuclear fusion that happens during its lifespan. It's always happening in the core of the star, because it's happening in the core of the star. Okay, this is kind of what runs the star. Okay, and so this process that happens, it happens inside the nucleus of an atom. So we're talking about inside the core of a star, and then inside of an individual atom, in the nucleus, you have this nuclear fusion process happen. And this process is so much more than produces so much more energy than anything that happens on Earth. So much. Look at all those O's I put in there. So, and I capitalized it. So much more. Because it's a star, that's what's running, for example, our sun, that's what's running our solar system. And we're able to see these stars from millions of light years away. And that energy is so much more than anything we can produce on Earth. So here's going to be an example of what fusion looks like. Okay. So that was an image, right? And so now let's talk about what these things actually are. Okay, and so this is the fusion process happening inside our star. And so we'll watch the GIF one time through to see what's going on, and then I will give everything names. So these two red P's are protons of hydrogen atoms. Okay, it emitted some subatomic particles, don't need to worry about, and now it's a proton in a neutron, and it is a hydrogen. It's still hydrogen, but it got another proton added to it, and this time it's going to emit energy. Now it's got another proton coming in, and now we formed helium and sent two protons off in hydrogen. So again, two hydrogens coming together, okay, and it forms a stable hydrogen atom. Then we have another hydrogen proton coming in that forms an unstable, and it emits that energy that I was talking about. Then we have two of these in the core of a star collide. It forms a helium atom, and now we have two hydrogens emitted. So what happened here? We formed from two hydrogen atoms, okay, we formed, right, we have two hydrogens forming heliums, and then those heliums come together to form a stable helium atom. Okay, and so that means we're coming from a small atom, and we're progressively getting into a bigger atom. And so that's what's happening. So this is a helium, an unstable helium atom, emitting energy, and two unstable helium atoms coming together and making a stable helium atom and producing or sending off protons. Notice how we never lose, after this one, we never lose the protons and the neutrons. They always stay the same. Okay, so we started with one proton and one neutron. We had two protons, one neutrons, and we finish here with four protons and two neutrons. The amount of matter in the nucleus is conserved, and that's very important. Okay, so that's a GIF. So now let's kind of look at a picture of the process a little bit closer and slow it down. So notice how protons are never lost. We never lose any matter here. What happens is when these collide, this proton becomes a neutron, okay, and we collide here, we lose energy, So we have hydrogen, 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 hydrogen. They come together. It forms a stable hydrogen with a hydrogen proton, comes together, gives off energy, forms a helium. That helium hits another helium. Now these are unstable heliums. But notice where we start here. From this process on, right here, that second process, we have the same amount of protons, 4, 1, 2, 3, 4, that we end with, and the same amount of neutrons, 1 and 2, 1 and 2. And so in a nuclear process, the matter is conserved. We do not lose any protons, and we do not lose any neutrons. That's nuclear fusion. It produces the energy. It also is what produces our new elements. So that you're seeing hydrogen being turned into helium through the process of nuclear fusion. So let's see what else we can add to this. Right? So now we're putting it into words. This is a written format where I just expressed it to you verbally and graphically with those pictures. So here's a written explanation of nuclear fusion. By combining smaller atoms, new bigger atoms are created. New elements might form, but the protons and neutrons remain the same before and after. It's the conservation of matter. This is what produces all the elements in the universe. Well, not quite, but close. So all the elements are produced all the way up to iron. Any elements up heavier than iron are not produced through this nuclear fusion process. But the fusion happens all the way up to the element iron in stars, and in the core of stars, we are producing elements constantly, bigger and bigger elements. So the question is, we have gold, we have silver, we have all these elements on the periodic table that are bigger than iron. So where did they come from? Well, we are going to find out. A supernova, and remember, if you go back to the picture of the life cycle, this was one of the last steps of a star's life cycle, the supernova. This is when a really massive star can't fuse elements. So they can't fuse elements anymore, mainly because they don't have enough mass or energy. So what it ends up doing is it has no choice, but it comes in on itself and it creates a massive explosion. And from this massive explosion and all of this energy, this is where all of the heavier elements are formed. All those heavier elements than iron come from something we call a supernova. Okay, and so if we come back here, the second point of this standard, the big idea here, is that how do stars go through their life cycle producing elements? Nuclear fusion in the core produces all the elements from hydrogen. Sorry about this. We'll let it pass. Nuclear fusion is what takes this hydrogen and turns it all the way into iron. And then once we get to iron, stars can't fuse that iron anymore. And so the next option in their life cycle is they're so big and they so much energy that they comes all in on each other, and then this huge explosion happens. And when this huge explosion, every element higher than iron is formed. And so those are the two main concepts: how do elements produced, and how do we study those stars? And these notes tell us that and help us instruct us. And so you need to communicate the information to me in about that information, in the idea of this concept, cross-cutting concept throughout all of science. You will see this conservation of matter, where matter cannot be created or destroyed. And in this specific example, in stars, it's the protons and neutrons that stay the same in fusion. Okay. Before and after. We have new elements, but we have the same amount of protons and neutrons. So now, we talked about how hydrogen forms into helium, okay, and then helium will eventually form into carbon. But we want to know how, if we want to extend this, go a little bit next level, we want to know how do the elements between carbon and iron form. And there's two ways to go about this. There's more complex nuclear fusion. One is going to be basically a carbon cycle of fusion. And so you notice here, we get a carbon atom, and it gets a proton added to it, and it becomes unstable nitrogen, okay? And that nitrogen emits energy, and then over a while, that unstable nitrogen turns back into a different type of carbon, okay? Now that carbon is sitting there, and it gets a hydrogen added to it. Again, And so then that hydrogen makes it now a stable nitrogen. And when it has this process, it gives off energy. And we come down here, and we have a hydrogen added to that nitrogen. And now we have an unstable oxygen that gives off some energy. And so that unstable oxygen becomes an unstable nitrogen. Okay. And that unstable nitrogen gets hit with a hydrogen. Okay, that unstable nitrogen gets hit with that hydrogen atom, nucleus, sorry, proton, the hydrogen proton. And what happens now is now we have a stable carbon that has now left us an helium atom out here. And so that's kind of a more complex version of nuclear fusion that happens inside stars. And the product at the end is a extra helium. But really what's happening is carbons being fused with mostly. Or the other version, which is you just have higher elements than carbon, and you just take a helium atom and you fuse it, and it keeps getting bigger and bigger and bigger and bigger. So every time it fuses with helium, it gets larger and larger. So both those are things that are happening above the produced atoms above carbon in stars. You're either adding just the helium instead of fusing hydrogen and hydrogen together. Now you're fusing helium with a bigger element, or you're going through a carbon type cycle where you keep fusing a hydrogen with a carbon or bigger atom to get a product of helium. And so those are the two kind of complex. And so if you look here for this one, you can kind of see you add 4 hydrogens to a helium, gives off a lot of energy, and we get a final product of a new helium with a carbon atom, and it kind of cycles. So this is standard 1.3, and this is a very helpful look into what you will need, the nuts and the bolts, exactly the meat and potatoes, the things that you need to know for this standard. Again, you also remember you have to communicate this information to me in multiple formats, so keep that in mind, but use this as a tool to help you.